This video will be your introduction on the learning target regarding the mole. The learning target is I can use moles to convert between any unit of measurement for any substance. We won't get through this entire learning target really with this one video, but it'll be your introduction and kind of your foundation that we'll build on. So the mole is our real beginning of calculated math in chemistry. And the mole is really here as a bridge for us between massing something and counting something. So when we're dealing with any kind of substance, the chemist can't actually count the individual atoms of that substance, right? And if I have a pile of water, I can't say like, no, I have 12, molecules of water right here. That's not something we can do. But the problem is that everything that we've done so far in chemistry has to do with counting, right? We've done all of our balancing of chemical equations and our writing of formulas, and those all had to do with how many, right? There's 2 H's for every 1 O in water. If I make sodium chloride, it's 1 sodium for every 1 chlorine. If I'm going to balance something, I'm going to have to count up how many atoms are on each side to make sure the counts are equal. That's all well and good when we're talking about what we've done so far, making formulas and balancing. But when we want to get into lab, the problem is we can't count. And so now we are working with mass or grams. Okay, if I have 10 grams of water, I have to relate that somehow to the chemical equation in order to be able to predict what's going to happen from start to finish. So the mole is a convention that chemists came up with that allows us to determine and relate the amount of something and the mass of something. So when I say the word mole, what mole is it's like a really big fancy dozen. Okay, for chemists, 1 mole is 6.02 times 10 to the 23rd particles of anything we're counting. So if I said a dozen shoes, that would be 12. If I said a dozen eggs, that would be 12. If I said a dozen pencils, that would be 12. If I say a mole, it's always 6.02 times 10 to the 23rd. Okay, that number seems very arbitrary and random, but it's based on the atomic masses on the periodic table. So if I had 12 grams of carbon-12, so not all the isotopes of carbon, just the carbon-12, and you use the conversion factors between the AMUs and all of that, it would end up being 6.02 times 10 to the 23rd atoms. That's why we choose it. I'm going to show you a quick video that's not my video about the mole, and then we'll come back together.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So that gives you some of the foundational concepts for the mole and this idea that there's a relationship between mole and gram. Rather than saying I need 12 atoms of hydrogen, we talk about it as like a mole, as a gram, as how many grams of it we have. Same as when you go to buy deli meat. So the most important relationship in chemistry that we're going to continue to use is something called the molar mass. And the molar mass is just what is the mass of a mole. If I have a mole of something, what does that mass out to be? So if I have 6.02 times 10 to the 23rd of a thing, what is that mass? Okay. So the label for molar mass then is how many grams it is per mole. So grams per mole, similar to density. It's a relationship measurement essentially. And what's nice is this information is 100% presented to you on the periodic table. So those atomic mass numbers on your periodic table, like carbon's 12.011 and oxygen is 15.999. We've talked about that as being the average atomic mass of any given sample of an element, but because of the definition of a mole, 6.02 times 10 to the 23rd atoms in 12 grams of carbon-12, that also becomes the molar mass. So the molar mass, what is the mass of 6.02 times 10 to the 23rd of any given element? It's just the atomic mass on the periodic table. So if I'm dealing with compounds, all you would do to figure out the molar mass of a compound then is add up all of their molar masses of the elements that are in the compound. So if I'm dealing with sodium carbonate, for example, I have 2 sodiums, 1 carbon, and 3 oxygens. I would just look at the periodic table, find the atomic mass number, which is the same number as how many grams there are per mole, and then I would just add them together. So sodium is 22.990. I have 2 of them in sodium carbonate, so I'm going to multiply that out. Carbon's molar mass, if you look at the periodic table, is 12.011, and there's just 1 carbon in sodium carbonate. Oxygen's is 15.999. There are 3 of them, and then you just add them all together. Now, when it comes to thinking about these as measured numbers, I would say they aren't measured numbers because in the end, we're making a relationship, how many grams there are per mole. So we never round our final answer based on the precision of these numbers because they aren't considered measured. That's it. We're going to practice a lot of this. Go ahead and do the quiz and have a nice night.